Hey everyone, welcome back. We are starting a new chapter. We're starting the molecular compound chapter, chapter 4. And just as a reminder, in chapter 3, we dealt with ionic compounds. And ionic compounds are when you have things typically like a metal and a non-metal coming together. So something like sodium and chlorine, sodium chloride. We know that the sodium loses an electron and makes a positive one cation, and the chlorine loses an electron and makes a negative one anion. And they pack together in an ionic crystal where the positives and the negatives basically do everything they can to stick next to each other. And so this might be a cross section of a very small slither of an ionic compound. And this is very different than what we're going to see in this chapter. So, chapter 4 deals with molecular compounds. CPDS is just my shorthand for compounds, and this is typically when you have two nonmetals taken together. So if you had something like boron and fluorine, this would be a molecular compound. If you had something like nitrogen and chlorine, it would be molecular. And if you had something like carbon and oxygen, it would be molecular. And so on, something like carbon and hydrogen, that would be molecular. So you got two different elements here. Typically, they're both nonmetals. Now, technically, if you look at hydrogen on the periodic table, it's often written on the left-hand side with the metals, but there's really not a good place to put it. So some periodic tables place it on the right as well, and some of them place them floating in the middle because it doesn't really fit in either. So we're going to say that hydrogen is sort of an honorary nonmetal in this chapter. So whenever you see carbon and hydrogen, we're going to take that as being a molecular compound as opposed to an ionic one. One of the most famous molecular compounds, of course, is H2O, and that is water. And as opposed to sodium chloride, where the ions themselves are sort of dotted around in a crystal lattice, what makes a molecule is that they are discrete units. So if I take water and I draw it out, it has that bent kind of shape, and I'm going to draw sort of a red circle around it that represents the outside of the molecule. And when we have another water molecule, okay, it might look something like this. And if we have another water molecule, okay, maybe it looks something like this. And what we have, though, are these discrete units here, these things that I'm circling in red, and these we call molecules. So you can kind of reach in and you can grab the essence of water by grabbing one of these. Whereas if you look at sodium chloride, right, you can't really say there's a NaCl unit that goes together. So does this one go with this one, or does this one go with this one, or does this one go with this one? And we don't really have a good way to describe that. So instead of talking about a molecule, a discrete entity that exists all by itself, we talk about a formula unit. So basically, we draw a red rectangle around there and say, hey, that's the simplest ratio of the cations to anions, such that the charges cancel. Sometimes we might call it a molecule for short, but a formula unit is the proper name for it. I've gone to a clean slide here. Now, if we look at the water molecule, it looks something like this. And we normally draw a line between the atoms themselves. So this has a bond between the H and the O, and another bond between the O and the H here. So these are chemical bonds here. We're going to call these covalent bonds. And I guess the question is, what on earth is this bond? And in early representations, we would talk about kind of a hook and eye model. So we'd say the hydrogens have little hooks on the outside, and the oxygens have little eyes on the outside, and they just have to hook up so that all the eyes find all the hooks. And so if you had chemistry 100 years ago, you would probably talk about things like this. So carbon was thought to have basically 4 hooks on the outside, and something like chlorine was thought to have, a single hook on the outside. And something like oxygen was thought to have 2 hooks on the outside. Whether the hooks are eyes, that's a more advanced bonding theory. And they basically just come together so that all the hooks kind of hook together. And we're going to see that is not actually what's happening. There aren't really little hooks on the outside of the atoms, although that actually explains an awful lot of chemistry. But what we're going to see is it's coming from the sharing of electron pairs. There's a chemist called Lewis back in the 1920s who actually came up with his theory of bonding. And we basically said that it's the valence electrons that you have to worry about. And if you remember from the last chapter, the valence electrons, those are the ones on the outside of the atom. So if you have something like carbon, carbon is element number 6, and if you remember the electron configurations, it has 2 electrons in the first shell. The second shell can hold up to 8, so if we've got 6 electrons total, 2 go in the first shell, 4 go in the outer shell. And those outer shell electrons are what we call the valence electrons. And if you remember, the other ones that are tucked away on the inside are called the core. And so these electrons here are really what's going to determine how the atoms are going to bond together. And if you take something like silicon, so silicon is element number 14, I believe. And in sci-fi movies, silicon, often you hear about carbon-based life and silicon-based life. And the reason for that is that silicon's electron configuration is 2-8. So that's 10 electrons right there. There's 4 more remaining, so 2-8-4. And if you look at that, you've got exactly the same number of valence electrons. And so since that determines the bonding and the core electrons are basically just there on the inside kind of minding their own business, then we're going to expect that silicon and carbon would have very similar properties. So people have wondered, is there life on another planet where in place of the carbon atoms, it uses silicon. So I don't know about this, but here's little Alf here in the top right corner. I don't know if you remember that cheesy 1980s TV show. Alf was alien life form, and I don't know if they ever established what Alf was made of. I'm assuming it was carbon-based chemistry, but it could have been silicon-based chemistry, I suppose. So according to Lewis, Lewis defined the bond, or more properly the covalent bond, and this is the bond inside of molecules, comes from the sharing of pairs of electrons. So sharing 2 electrons, which we're going to call a pair, is what we're going to refer to as the bond. And we normally just write a line, something like that. So when we look at water and we write water, something like that, every time we write that line there, we are seeing a pair of electrons, and there's another pair of electrons there. And we'll come back and we'll draw these so-called Lewis structures later, but they're used to kind of explain what's going on. So instead of eyes and hooks, we've got valence electrons. So it's a little step up, I know, but hey, it's pretty darn good.